All right, Ivan, can you hear me okay?
Yep.
Great. So let's get rolling. Good morning, everybody. I hope you're having a nice week, whether you're joining from Marcus or the live stream. We are just continuing our work through chapter 4. There will be a review on Thursday and then again on Monday for critical points as well as inflection points. So I will send an email out about that. So if you're looking for more practice, in preparation for the chapter 4 quiz, then that will be coming up as well. So today we're going to be talking about inflection points. And this is sort of an extension of the work that we were doing last class. So last class, again, we were talking about critical points, which have to do with the first derivative. And today we're going to talk about inflection points, which have to do with the second derivative. But what you'll find is that throughout our work with inflection points, that some of the stuff we learned about critical points is going to come back. So we will have to use what we learned last week. So I'm going to go ahead and switch over to the doc cam here. Okay. And so we're going to start by talking about what is an inflection point. We did talk about this briefly in chapter 2 when we started learning about different things related to the second derivative. But an inflection point is a point on a function f of x where we change concavity. So if we look at this picture here and we look at the concavity of this graph, we see that this graph starts off from about here to here, right? This is concave up because it looks like a cup. And we know from previous work that when the function is concave up, that our second derivative is positive. And then on the right-hand side of our picture, we see that this is concave down. And we know from previously that the relationship is that the second derivative is going to be negative, where our function is concave down. And so our inflection point comes in right about here, where we're going to change from concave up to concave down. So that point where we change is called an inflection point. And at the inflection point, the second derivative equals 0. So in order for us to change from positive to negative or from negative to positive, we would have to go through 0. And so that is the relationship with this inflection point. We're looking for where we change concavity. And so we have to be a little bit careful about this as we go, but as long as the second derivative changes signs, then we have an inflection point, okay? So what does that mean for identifying inflection points, for working with inflection points, and all the types of things we want to do in terms of mathematically determining these types of things? So the process for thinking about and finding inflection points is step 1, determine where the second derivative equals 0, okay? So if you have an inflection point, then the second derivative will be 0 at that point, okay? This statement only works in one direction, which means if the second derivative is 0, it could be an inflection point, but it might not be. So we have to check. So that becomes step 2 of our work. And so we make sure that the second derivative changes signs. So signs, we're talking about positive and negative around the possible inflection point. Because if the second derivative changes signs, that means the function changed concavity, and we do have an inflection point. So how does this work, right? So we're going to start with a practice problem here, and we want to identify any inflection points of this function. So step 1 is we are going to find the second derivative and see where it equals 0. In order to find the second derivative, we need to start by finding the first derivative. So we find the first derivative, then the second derivative, and say, when does the second derivative equal 0? That's where we have our possible inflection points. Then we need to make sure we change signs. So just like the first derivative test, we're going to make a chart where we're going to put our possible inflection point on there, and we're going to test something to the left and to the right of our possible inflection point. Since we're talking about the second derivative, we are plugging our test points into the second derivative and recording the sign a little to the left and a little to the right of any possible inflection points. So that's our process. So I'm going to have you try this. I'm going to give you 2.5 minutes. So I want you to find the first derivative, then the second derivative, set the second derivative equal to 0 and solve. Then do test points on either side of any possible inflection points. If we change signs around that point, it's an inflection point. If we don't change signs, then it's not. Okay, so take 2.5 minutes, try it out, and then we will go through it together. Okay, take about 30 more seconds. All right. So again, we need to get to the second derivative. In order to do that, we have to go through the first derivative. So we have 6x squared minus 6x minus 36. Hopefully you're feeling comfortable taking first derivatives using this power rule, which comes up quite a bit. And then our second derivative here we're going to get 12x minus 6. So as a reminder, 36 is a constant, so the derivative of that is 0. So now for step 1, determine where the second derivative equals 0. So we set our second derivative equal to 0. We're going to add 6 on both sides. We get 12x. We have a 0 sum equals 6. So when we divide by 12, we get x equals 6 over 12, which can be reduced to 1/2. So 1/2 is the place where if we have an inflection point, that's where it will be. Okay, so x equals 1/2. This is our contender. How do we now check to make sure it's an inflection point? So this is where we are going to do a little number line, just like we did before. Here we're going to put in our inflection point, right? Our contender. We know that the second derivative is 0 at 1/2. That's how we solved it. So now we need to test something a little to the left and a little to the right. So again, you want to pick points that are going to be easy to work with. So I'm going to pick 0 to the left And so I'm going to plug 0 into my second derivative because I'm interested in the sign of the second derivative. So 12 times 0 is 0, minus 6 is negative 6. So when I test something to the left, it's negative. And then I'm going to pick something to the right. So I'll pick 1. 12 times 1 is 12, minus 6 is positive 6. So here I see that I change from negative to positive. It doesn't matter which way it changes. It could go from positive to negative or negative to positive. But in order for this to be an inflection point, the sign has to change. So since it does, x equals 1/2 is indeed an inflection point. How do I know that? Because if the second derivative is negative, I was concave down on the original function. And if it's positive, I was concave up. So I changed concavity around this point, which is the definition of inflection point. So this is sort of the common way that we check to make sure things are actually inflection points. And this is the process we use when we're just looking for inflection points. So let's try another that's like this one. Okay. So suppose that we have the function 3x to the 4th minus 4x cubed plus 6. I want you to find any and all inflection points of this function. So again, you're going to find the first derivative, use that to find the second derivative. Once you have the second derivative, you're going to set that equal to 0. You might have to do a little factoring in this one. This is a higher order polynomial. But once you find any values that make the second derivative equal to 0, then you will test them by testing something a little to the left and a little to the right on a number line chart. Okay, so take 2.5 to maybe 3 minutes, try this out, and then we will go through it together. Okay, take about 30 more seconds. Okay. So we start by finding the first derivative because we need to go through the first derivative to get to the second derivative. And so here again, we go term by term. The derivative of 3x to the 4th gives us 12x cubed minus here 3 times 4 is again 12x x squared. The derivative of 6 is 0 because it's a constant. Now for our second derivative, here we're going to get 36x squared because 3 times 12 is 36 minus, now we have 24x. Okay, so we want to know, when does the second derivative equal 0? And there's different paths you can take at this point. You can use the quadratic equation. You can factor it. And if you factor it, there's more than one right way to factor this. So if you didn't do the next step exactly as I do, but you still ended up with the same possible inflection points, then I'm sure whatever you did is probably great. Okay. So here, when I factor this, I'm going to pull out a 12x. Okay. You can also factor this by only pulling out an x and you will still get the same result, but this is just how I did my workout. So if I pull out a 12x from the first term, 36 divided by 12 leaves me with a 3. X squared divided by x leaves me with an x. And then over here, I'm left with a 2. And again, there's different ways you can factor this. So you may have factored this, but done it slightly differently. That's totally fine. So now I have 2 factors equals 0. So I need to set each of those factors equal to 0. So if 12x equals 0, that gives me x equals 0 as a possible inflection point. And if I set 3x minus 2 equal to 0, that gives me x equals 2/3 as a possible inflection point, because I would add 2 to both sides and then divide by 3. Okay, so these are my possible inflection points, but now I have to test them. So again, I'm going to set up a number line, and I'm going to add these points in order as they would appear on a number line. So I have 0 and 2/3. I know that the second derivative is 0 at those points. So now I want to test something to the left of 0, between 0 and 2, and to the right of 2/3, right? So again, I'm going to pick my test points to be convenient for testing here. So I'm going to start by testing -1. Now, again, there's a couple different ways you can test these. We want to find the sign of the second derivative at -1. So you could just plug it right into this function and see is the result positive or negative, or you can plug it into each of the factors to see if you're going to get a positive or negative result. You should get the same result either way. So if I plug a -1 into the 12x factor, that's going to give me something that's negative. And if I plug a -1 into 3x minus 2, that's going to give me -5. So that's also negative. Negative times negative, that's going to give me something positive. So that's one way. The other way is I could plug a -1 in here. -1 squared is +1. So I have 36, and then the -1 plugged in here will make this plus. So 36 plus 24, that would give me positive 60. So I would also get a positive result. Either method will give you the same positive output. Okay. Now I want to test something between 0 and 2/3. So I'm going to test 1/3. If I plug a 1/3 into 12x, that's going to give me something positive. If I plug in a 1/3 here, 1/3 times 3 is 1. 1 minus 2 is negative. So I have positive times negative, which is negative. And then I want to test something bigger than 2/3. So I'll test a 1. So if I plug a 1 into 12x, that gives me positive 12. And then here, if I plug in a 1, 3 times 1 is 3, minus 2 gives me positive 1. So positive times positive is positive. So what I see now is that for both 0 and 2/3, the sign changes around these points. And so what that tells me is that both of these points are inflection points. Okay, if this had been negative, negative, then it would not be an inflection point. Or if it was positive, positive, it would not be an inflection point. But as long as it changes around your possible inflection point, then it is indeed an inflection point, because the change of sign indicates a change of concavity on the original function. Okay. So now that we sort of have a sense of the process of testing inflection points, I want to sort of give you a common way in which this is asked for on homework and sometimes on quizzes. So commonly, the idea of finding inflection points is paired up with this idea of finding local maximums and minimums. So this is a very typical type of problem that would involve both of these things. So find all local maximums, minimums, and inflection points for the function 2x cubed plus 3x squared minus 180x plus 5. So again, we really need to think about how we use the first derivative to find critical points, how we use the second derivative to identify possible inflection points, and then what we need to do to determine are the critical points local maxes and mins, and is the inflection point actually an inflection point? So I want you to try this out. I'm going to give you 3.5 minutes because there's sort of a lot of steps here. If you are getting confused about critical points and inflection points, at the very least, make sure that you are finding the first derivative and the second derivative and setting them both equal to 0 to solve, right? So those are things that hopefully skills that you are comfortable doing now from chapter 3. And if you are able to think about how we then classify critical points and check inflection points, go ahead and do that. Okay, so take about 3.5 minutes, and then we will go through it together. Okay, take about 30 more seconds. Okay. So once we start doing problems that involve a lot of different processes at once, we have decisions to make. And one of the things I'm going to recommend is just trying to think about how you organize your work, right? So you want to be able to go back and check things, if something goes wrong, but also to really just keep your thoughts organized. So we're going to be dealing with the first derivative and the second derivative here. And so I'm going to start by doing my first derivative. So here, when we take the derivative of this function, we get 6x squared plus 6x minus 180. Okay. And so now I'm going to ask, what do I want to do with the first derivative? Well, the first derivative, I need to do two different things. I need to use it to find the second derivative, and I need to use it to find critical points. So I'm going to find critical points first. You can certainly find the second derivative first. It doesn't matter which order we do this. But for me, the way I'm going to organize this is by going sort of down below this work to see what happens when I set this equal to 0. Okay, so I'm going to factor this. And when I factor, I'm going to start by pulling out the 6, which was the leading term here. So I'm left with x squared plus x minus 30 equals 0. And then when I factor that down, I get x plus 6, x minus 5 equals 0. So that gives me two possible critical points, right? Critical points. I have x equals -6, which is going to make this first parenthesis equal to 0. And I have x equals 5, which is going to make the second parenthesis equal to 0. Now, I know in order to finish this question, I'm going to have to determine if my critical points are local maximums, minimums, or neither, which means I'm going to have to use one of the tests that we talked about last week. But before I do that, I'm going to move on to the second derivative, because the second derivative is also one of the ways that I can look at these critical points. So I'm going to go ahead and take the derivative of the unfactored version here. So I get 12x from the first term. The 2 comes down to multiply the 6, plus 6. And then the derivative of 180 is 0 because it's a constant. So again, I need to do a couple of different things with my second derivative. One of the things is identify possible inflection points. So if I take 12x plus 6 and set it equal to 0, I can solve for 6 and I get x equals -1/2. So I subtracted the 6 over, divided by 12, I get -6 over 12, which is -1/2. And so the question is it an inflection point, right? So I have a possible inflection point, and then I still have two critical points that need to be classified. So I'm going to do this in a way that I think will maximize my efficiency of solving both of these problems. So I'm going to use the second derivative test to classify my critical points. Now, you don't have to use the second derivative test. You can use the f of x test, or you can use the first derivative test to classify them, and you will get the same answer. But I'm going to talk through the benefit of using the second derivative test in this case after we have done it. Okay, so for the second derivative test, I need to plug in my critical point into the second derivative. Okay, so I have 12 times -6 plus 6, and that gives me -66. If your second derivative is negative at a critical point, that means the original function is concave down, which makes that critical point a local maximum. So x equals -6 is a local max. I also want to test my other critical point. So I have 12 times 5 plus 6 equals +66. So if your second derivative is positive at the critical point, it tells you that the original function is concave up, and it makes that critical point a local minimum. So now I know what my critical points are, right? So I've done this part. And the reason why it's beneficial to use the second derivative test here is because we can also use these values when checking the inflection point. So let's have our number line. Let's throw the -½ on there. We know that at -½ the second derivative is 0. We need to test something to the left and to the right of -½ Well, these critical points happen to be one to the left and one to the right, right? So -6 is to the left of -½ and we found that to be negative. And then +5 is to the right of -½ and we found that was positive. So I'm able to use the same values that I used to classify to also check my inflection point, right? And I see that it does change signs, so it is indeed an inflection point. So it does save me a tiny bit of work to use the second derivative test to classify my critical points, because then I can use that work to also talk about the inflection point. And again, it's not too much of a stretch because I already had to find the second derivative. So in this type of problem, I do recommend that you use the second derivative test to classify critical points, but you don't have to. You could certainly use one of the other tests and then still do this test on your own, where you pick something a little to the left and a little to the right, and you will get the same results. Okay, so our final solution here is that we have a local max at -6, a local min at 5, and an inflection point at -1/2. Whenever you have a problem that's sort of this long and complicated, I do recommend that if you are able to, that you check the graph of the original function to make sure that it agrees with what you're saying. And so I graphed this on my calculator here. I'm just gonna put this up here. The general graph looks like this. Okay, so I'm going to go back so you can see here, this is the 2x cubed plus 3x squared minus 180x plus 5. And I see that I do have a local max right about -6. So if you count over, that's a local max. I have a local min at roughly 5, and the inflection point is right near 0-ish. So -½ if I were to zoom in is going to be where that inflection point is. So that agrees with all the work I did. And it's an easy way to check it is just to graph it and make sure it matches. Okay. So those are the common computational types of problems that we do with inflection points. There's other sort of more analytical problems that we do as well to sort of make sure that we can use the definition of critical point and inflection point to help us understand what's happening in a situation. And so we're going to do some analytical problems now that really help us think about how we apply these definitions. So the first one we're going to look at is we want to find a formula for a cubic polynomial in the form ax cubed plus bx squared plus cx plus d that has a critical point at x equals 4 and an inflection point at 2, 5 and a leading coefficient of 1. So I want to say a couple quick things before you try this. First, I want to talk about a leading coefficient. So if it's been a while since you've done algebra, the leading coefficient is the number in front of the term with the highest power. So that means that a leading coefficient of 1 automatically tells us that a equals 1 because the highest power here was 3. The critical point is at x equals 4. This is different than what we normally do. Normally, we solve for that x value. So I want you to think about how we would use the x value if we knew it was a critical point. And then the second thing I want to mention here, we have the inflection point at 2, 5. So when we have this coordinate 2, 5, that is where the inflection point lives on the original function. So if you go over x equals 2, y equals 5, that's where the inflection point is. Notice that in the other problems we have done for inflection points, we only consider the x value. So think about that in your work. Okay, so what I want you to do is I want you to find the first and second derivative of this function in general. You can plug in the 1 for a. And then once you have the first and second derivative, think about how you can use this other information to try to solve for b, c, and d. Okay, so I'm going to give you about 3 minutes to try it out. Do your best, and then we will go through it together. Okay, take about 30 more seconds. Okay, so let's remember our ultimate goal here is to solve for A, B, C, and D. And we already have the value of A just from the setup of the problem. As I mentioned, I wanted you to find the first and second derivative and then determine how we can use this information in conjunction with these functions. So when we take the first derivative, we know that A is 1. So the derivative of this first term we can write as 3x squared because 3 times 1 is 3. For the next term, when the 2 comes down, we need the 2 and the b because we don't know the value of b yet. So we get 2bx to the 1. And then the derivative of cx is c, and the derivative of d is 0 because it's a constant. Now, similarly, when we find the second derivative, Here, the derivative of 3x squared is 6x. The derivative of 2bx is 2b, because 2b is the constant. And the derivative of c is 0. So we have our first and second derivatives. And now we want to think about how we can use the information in the problem to help us solve these things. And so as a reminder, we are told that we have a critical point at x equals 4. And I'm just going to put f prime of x because critical points have to do with the first derivative. We also know that there's an inflection point at 2, 5. So I'm going to write f double prime of x because I know that the inflection point also relates to the second derivative. So what do I know about critical points? I know that we have a critical point if the first derivative equals 0. So what that means is if I were to plug a 4 into the first derivative, that the derivative would then have to equal 0. Okay. What do I know about inflection points? Well, if I know I have an inflection point, then if I were to plug the x value of the inflection point into the second derivative, that would make the second derivative equal to 0. What I notice, however, is that the first derivative has 2 unknowns, and the second derivative only has 1 unknown. And that unknown is also part of the first derivative. So I'm going to actually start with the inflection point information and then work my way back. So if the inflection point is at 2, 5 on the original function, what that means is if I take the x value, which is 2, and plug it into the second derivative, that the second derivative would have to equal 0. Okay, because remember, when we look for inflection points, we are only identifying the x value. This 5 is a point on the original function, not on the second derivative. So now I have 6 times 2 plus 2b equals 0. So that's the same as 12 plus 2b equals 0. So if I subtract the 12 over and then divide by 2, I find that b equals -6. Okay, I'm able to solve for b. Now that's particularly helpful because b also shows up in the first derivative, which means I can now rewrite my first derivative with that value in it. So I have 3x squared. Now, if I substitute in a -6 here, I get -12x plus c. So now I only have 1 unknown because I plugged in the value of b. So now I can use the fact that I have a critical point at x equals 4, which means if I were to plug in a 4 into my first derivative, that would have to equal 0 because it's a critical point. Okay, so 4 squared is 16 times 3 gives me 48 minus 48 plus c equals 0. 48 minus 48 is 0. Those cancel. So I get c equals 0. Okay. So now I have a, b, and c. So if I put those together, right, the things that I already know, then what does my equation look like, right? I have 1x cubed minus 6x squared. C is 0, so this term goes away, plus d, right? So d is the only thing I don't know yet. And so that's where this point comes in. This is a point on the original function, which means that when x is 0, y is 5. So I can use that to solve for d. I have 5 equals, so that's the y value, 2 cubed minus 6 times 2 squared plus d. So I have 5 equals, now 2 cubed is 8, minus, now 2 squared is 4 times 6 is 24, plus d. 8 minus 24 is -16 right here. So I add that over and I get that D equals 21. Okay, so I'm able to solve for D by using the point that's on the original function, but I'm not able to do that until I have all the other values. So again, this is a tricky problem overall. I mean, it's not super straightforward. You really have to think about how we use our definitions and our analysis and what we know how to do to put everything together. And I'm fairly certain there's at least one problem like this on your homework. So make sure that you sort of have the steps outlined so when the numbers change, you're able to do a similar type of problem. Okay. So this is sort of the merging of computational work plus analysis. The next set of questions we're going to look at are all analytical. So that means we're taking what we know about the properties of first and second derivatives and trying to answer questions when given information instead of functions. So what does that look like? Okay. So suppose we have the following information regarding the first and second derivative. So what does that mean? This first charted line is the first derivative. So we see that the first derivative equals 0 at 0. The first derivative equals 0 at 2. And then we have the sign of the first derivative in each of these intervals. Then down here, we have the second derivative. The second derivative equals 0 at 0. The second derivative equals 0 at 1. And then we have the sign of the second derivatives on the second charted line. And so what we want to do is we want to use these two charts to talk about where we might have critical points and where we might have inflection points, and really just any other information we know based on the information that we're given. So what I'd like you to do is take about 2 minutes, think about what we know from this chart, write down anything you think is relevant that might help us in sort of understanding the behavior of this function. And just as a reminder, y prime is the same thing as f prime of x. So this is just the first derivative, and y double prime is the same thing as f double prime, so the second derivative. So this is all information about the first derivative. This is all information about the second derivative. This is what's happening at 0, 1, and 2. So take about 2 minutes, like I said, and jot down anything you think we can figure out about critical points and inflection points based on this information here. Okay, take about 30 more seconds. Okay. So what do we know here? So the first thing I would notice here is that the first derivative is 0 at 0 and at 2. So that tells me I have critical points at x equals 0 and x equals 2. So that means I should pay attention to what's happening around those points. So I notice that to the left of 0, my first derivative is positive. To the right of 0, so at 1, my first derivative also positive. And then to the right of 2, it's negative, right? So what I noticed is that it didn't change, right, when I looked around 0, which means 0 is not a local max or a local min. So we call that neither for now. But it did change around 2, okay? It went from positive, which means the original function's increasing, to negative, which means the original function's decreasing. So if you have a function that goes from increasing to decreasing, that makes it a local maximum. So 2 is a local maximum. Okay, so that's really good information that I get from the first derivative. I can also see, right, where my original function is increasing and decreasing. So I have something increasing and still increasing and then decreasing, right? And now for my second derivative, I see that the second derivative is 0 at 0 and at 1. So I could have an inflection point at 0 and at 1. So in order to check that, I want to figure out what the sign of the second derivative is here. So here the second derivative is less than 0, so it's negative. And then in this little area, it's positive, and then it's negative again. So what I notice is that it does change from negative to positive and then positive to negative. So both 0 and 1 are inflection points. Okay, and then I also know the concavity of the original function because of the sign. So if the second derivative is negative, the original function is concave down. So that's true here and here. And then when it's positive, I'm concave up. Okay. So what does that mean in terms of what this looks like, right? Like if I wanted to sketch this picture, what would that look like? So let's go ahead and take a stab at this. I'm going to put this up here to draw on. Actually, you know what? I'll put it underneath. That'll make it a little bit easier. So I noticed that I have things that 0, 1, and 2 are sort of the intervals that I'm looking at. So when I start drawing my picture, right, I want to make sure that those are sort of labeled on here. Now, I know that I'm increasing to the left of 0 through 0, and I'm increasing all the way until I get to 2, right? But I also know that I have an inflection point at 0 and at 1, where I start concave down, then I'm concave up, then I'm concave down. So that means I have a weird flat spot at 0, where I'm changing from concave down to concave up, right? So I kind of flatten out. I do something like this, right? So here it flattens out enough that I have a critical point, but not enough that it becomes a local max or a min. But I do also change concavity, right? And so then here, what was going on at 1? I'm still increasing, right? Another sort of weird flat spot. I have to change concavity. And then I have to end up with a local max somewhere over here. Oh, sorry, missed my picture. So I do have to make sure that I'm changing concavity as I think about this, but I also need to make sure that my local max ends up at 2, right? So I'm concave down here, right? I'm concave up sort of in between, and I'm concave down here. It's not perfect in terms of a sketch because I kind of messed up this little bump here, but I can see the properties here. And what I can do is I can use those to talk about the places where I have these particular things. So notice that we did have x equals 0 as a critical point, but it ended up not being a local max or min, but it did end up being an inflection point. So that's where this sort of weird flat spot comes in. We need to change concavity, but it's not a local max or a local min. Okay, so using these types of charts is another way that we do analysis on first derivative information and second derivative information. Another way that we analyze some things is going to be with a graph. So we've seen this graph before. We used it in a different way, but now we're saying, okay, suppose that we have a graph of the derivative. And the way we used this before was to find critical points and local maxes and mins. And now we're saying, how can we use the graph of the derivative to find the inflection points of the original function? Okay, and so we have to really think about, what does it mean to find an inflection point? Well, we need to have information about the second derivative, right? And so that means, how do we use the first derivative graph to give us information about the second derivative, which would then give us information about inflection points on the original function? So there's a lot of different relationships interacting here, and they're not all super straightforward. So we really have to think about what we need to know, what we need to look at to talk about the second derivative and what it tells us about the second derivative, so that we can then use it to link back to the original function. So I want you to think about this. I want you to take 2 minutes, see if you can figure out what kind of information we can get about the second derivative. And then once you've figured out what kind of information we can get about the second derivative, think about if we might be able to use that to talk about inflection points on the original function. Okay, so take 2 minutes and then we will go through that together. Okay, take about 30 more seconds. Okay, so let's think about how we can use the first derivative to give us information about the second derivative. So one of the key things from those relationships, which we started back in chapter 2, is we said that if the first derivative is decreasing, that tells us that the second derivative is negative. So whenever the first derivative is decreasing, so going in the downward direction, the second derivative is negative. And we also know that when the first derivative is increasing, the second derivative is positive. Okay. And then finally, we know that when we change from increasing to decreasing, that is where the second derivative is going to be 0. That's where we have a slope of 0 from our horizontal tangent lines. Okay. So that's the information we can get about the second derivative using the first derivative. So then how do we take that and think about the original function? Well, we're interested in the inflection points of f of x. We get inflection points when the second derivative is 0 and when we change concavity, where the sign of the second derivative changes. So we notice that in all the places where the second derivative equals 0, we change signs around each of those points, which means that all 3 of these points are inflection points. So we're going to have an inflection point at each of these x values. So let's look at approximately where these are going to be. Actually, we'll just write inflection points. So inflection points, critical points, these are all characterized by their x values. So we're just approximating where this is happening, and it doesn't have to be perfect. So this is approximately negative 1.5, right? This looks like it might be, I don't know, 1.75. And then over here, maybe 4.75, something like that, right? But we can see where these happen. And so we find our horizontal tangent lines on the first derivative to help us identify where the second derivative equals 0, which then helps us understand where f of x has inflection points. So the key starting step is really thinking about where is the derivative increasing and decreasing, and where does that change, right? So by looking at where the derivative is increasing and decreasing, we know something about the sign of the second derivative, which helps us figure out where it crosses through 0. Okay. So unsurprisingly, the next example, we're going to look at a table. This got cut off, so I'm going to read you the instructions and then flip the page to see the table. So suppose that f of x is a continuous function that is differentiable. Given the table of values for f prime of x, determine the most likely place or places that f of x would have an inflection point or points, depending on how many we find. So here we have a table of derivative values. This is the same one we worked on before to find critical points. So as a reminder, we had a critical point at x equals 6, because that's where the first derivative was 0, and also between 10 and 12, because we saw that the derivative changed from positive to negative. But now we want to use these values to figure out where we might have an inflection point. So similar to the graph, we need to think about how we evaluate the first derivative to give us information about the second derivative, and then how we translate that information about the second derivative to talk about the original function. So take about 2 minutes, see what you can come up with, think about what we did on the graph, and then we will go through it together. Okay, take about 30 more seconds. Okay. So again, what we're looking for is we're trying to figure out the sign of the second derivative by using properties of the first derivative. So what I'm looking for here is where the first derivative is increasing or decreasing. So -14, -8, -4, 0, 5. Those values are all increasing, right? They're increasing because they're becoming less negative and then they transition to positive. If the first derivative is increasing, that tells me that the second derivative is positive, okay? And then I notice that I have 5, 2, -1. So those values are going down. So those values are decreasing. If your first derivative is decreasing, your second derivative is negative. Now, in order for a continuous differentiable function to change signs from positive to negative or negative to positive, it has to go through 0. So the place where we change what's happening is the most likely place that we go through 0. So if we are trying to identify the most likely place we have an inflection point, it's going to be the point where we change signs in the second derivative, or where we change from increasing to decreasing or decreasing to increasing in the first derivative. So the most likely place that the second derivative equals 0 is at x equals 8, which means that that is the most likely place that f of x has an inflection point. Okay, so again, we're using all the different properties of things like inflection points and the first derivative, as well as relationships between the original function, first derivative, and second derivative, to analyze all these types of things with each other. So if you are having a lot of trouble putting the pieces together, you may need to spend a little time just organizing these relationships into one place, either in a chart or on a page, to really understand how they interact. Okay. So that's our last example for today. So we'll stop here. On Thursday, we will learn about global maxes and mins, but definitely try out some of the homework on inflection points, tonight, tomorrow, before you take the mini quiz, and then we will pick up with section 4.3 on Thursday. So have a great rest of your day.